in terms of units of meter cube, your N refers to number of moles. And yes, in physics we do have moles. And R is your gas constant 8.31. And T is temperature in units of Kelvin. Okay? This is a constant. I'll tell you that later. I can't. Gas constant actually. The full unit I'll let you know later as we define this. But basically you can find the units of R. Okay, basically you can just find it from here. Just play around with that. So you get PV unit divided by number of moles. Okay, unit of number of moles. And in terms of temperature, you can actually find a unit of R directly. So this will probably be Pascal, volume is meter cube, number of moles, and then temperature in terms of Kelvin. So you can make a guess or something like that. Cool? Okay, so this gives you your gas equation. So if something behaves like this, then obviously it's a gas. But let me just say something about this temperature in Kelvin. Now, temperature in Kelvin is not like a degree Celsius. There is a conversion equation, and the conversion equation is this. So temperature in Kelvin, okay, is equals to 273 plus whatever that you desire to convert in degree Celsius. Okay, so it is 273 plus degree Celsius. Now, having said that, let's say, for example, for 30 degrees centigrade or Celsius, you want to convert to Kelvin, what do you think you should do? I just mentioned that. What do you think you should do? Yeah, you just add 273. So temperature in Kelvin, okay, is equal to 273 plus 30 degrees. You end up with 303 in Kelvin. So this is the equivalent. Any questions on this? This one, the year 4 should have a problem. This the year 3 should have. Yes. Yes, you actually have to use this Kelvin in the equation PV and RT. You don't have to take it in 2 dB like 270.15. You mentioned that. No need. Estimate will do in your competition. But if you are doing specialized paper, you may want to include the 0.15. Not critical, okay, for your competition. So far, so good? Can? Now, yes. Okay. So let's come back to this original intention that I have. So for gases, we are very interested in how we do work on the gases. Okay? So let's say if we are able to put the gases in the syringe and we press the syringe piston all the way down. By that, we are actually doing work on the gases. So if there is a compression of salt and we do work, okay, and it's compressed. So obviously, if it's compressed, there is positive work done on the gas, and we call it plus. Now, this is during compression. Do you need to do work when my gas expands? When this piston is expanded, do you think you need to do work? No. So here, because the gas itself will automatically expand out, so the work on is automatically negative for expansion. Okay? So that's the reason why work done on gas for expansion negative, work done on gas during compression is plus. So far, this first row, is it okay? Yes. Cool, huh? Now, there is another term that you need to know, which is work done by the gas. Okay, sometimes we ask work on the gas, sometimes we ask you what is work done by the gas, but generally speaking, work done by the gas will be opposite to the work done on the gas. So if work done on the gas is positive during compression, it will be minus for work done by the gas. Okay, that's obvious. When you compress it, the gas does nothing. Okay, but it's totally subtracted to you, so this will be minus. And for expansion, the work done by the gas will be plus. That's obvious. So again, it's opposite to the result obtained above. So any questions for this? Yeah? Is this okay? Cool, huh? Now I'm going through very, very slowly. So continue. Now, I have to mathematically describe what work done is in formula, whether it is work done on or by as hold that minute. So your work done, actually according to your year 3 work, is equal to force times distance. Now, basically I can make use of pressure, and for the year 4 you'll be more lucky because you know more. For the year 3 work, you don't, okay, you just have to take my word for it that force is equal to pressure times area, and this will be covered in your assignment 6, and then times the distance. Now, from work done equal to force and distance to pressure concept, this is another 50 to 100 years apart. So this second line you have to really picture them. Okay? Now, you realize that when I convert force equal to pressure area, this whole thing can then be converted to pressure times volume. So my work done is actually equals to P times volume, PV. Got it? P means pressure. Okay? Now, because I have got this W equal to PV, I can actually, let's say for example, if my pressure is constant, okay, and I take a small change. Now a small change in mathematics is actually called delta. So I'm just going to write, okay, my small change in work done would then be equals to, if my pressure is constant, is equal to pressure times change in volume. But this pressure has to be constant. And sometimes, okay, my volume is the one that is constant, okay, then my pressure being changed, so I can also write V change in pressure. So it depends on context. Which one is it that you are using? Okay? But in general, work is equal to pressure times volume. Very important formula. Cool? Is this okay with you? Yes. Anyone lost already? Okay. Now, on. So if you are okay, yeah. So, any questions? Okay. Now I'm going to now tell you the first thing or first law that you're going to be learning. Okay, it is called the first law of thermodynamics. Now this first law basically follows energy conservation theory. Okay, whereby energy is conserved and all the energy you put in will be the energy that comes out in essence. So in equation form, it's going to look like this. Okay, first law of thermodynamics. The energy you put to change the internal energy. So this is really your change in internal energy. And this internal energy is exhibited by whether it is PE, potential energy associated, or kinetic energy associated. This is equivalent to the energy that's very obvious that you put in. So the change in internal energy is equal to the energy Q. Okay. This is the energy that you put in, which is heat. Okay, related. And this heat energy that you put in will not only increase the internal energy and the exhibition of it, plus the work done on the system. So I have got this first law of thermodynamics, delta U, which is the change in internal energy, which is equals to Q2, the energy into the system, and the work that associates with it, if it does work. So Q2 plus work on. This is the first law of thermodynamics. Internal energy. That means it could be the kinetic energy has increased, and the kinetic energy on the left term must be, the increase is due to Q2 and work on, and you have to find what is this and what is this, and then later you combine them. So far so good. Yeah. Yes.
What's the Q2 stand for?
Q2 is really the heat energy you put into the system. So energy into the system.
So 2 stands for into.
Yes, to the system. So far, so good.
It's like work energy you put inside plus the work energy
On the system. Yes. So far, so good. Now we are going to go into Q2 later. What does this Q mean? Now Q can be figuratively, like for example, you put 200 joules, can be like this. You put 200 joules into the system. And then here your Q2, the system will just be plus 200. Could be there. Or from this system you take out 200 joules and your, obviously it will be negative. Can? Now let's understand Q more, because Q is a big broad topic. So far so good, gentlemen. You are making your notes, right? So until this stage, okay and all. Can. Now I'm going to just take it very, very slowly. So before we understand more, okay, let's refresh back your memory about certain things on Q, heat energy, which the year 4 should already have done. It relates something to this concept called the specific capacity concept. Okay, specific heat capacity, and then specific latent heat. These two concepts will be very important for Q2. Okay. Now, for specific capacity, this idea, okay, I'm going to just use a very simple elaboration. Let's say if I have an ice, let's say that you take out from the fridge at -4 degrees. Do you think this ice at -4 degrees is going to start melting immediately? No, it won't. When you take out, the first thing that you observe is that the ice will be sticking to your hands. Okay, it won't immediately melt. And that's quite dangerous because it can cause injury if it's dislodged. So if I plot a temperature time graph, the time could be in seconds. And then this is my temperature. I will begin from -4 degrees, and then later what happen? It will increase in temperature as heat is absorbed, all the way down to 0 degrees. At this stage, your ice will still be at solid state. Correct, gentlemen? Now, because your ice is going to be at solid state, all it does is just absorb energy into the ice, but this guy doesn't do anything. It is not so obvious. The ice has become warmer and warmer. In this case, this kind of condition is called specific heat concept. That means the heat energy is absorbed. Temperature rises. Okay, for this specific concept, you realize that temperature rises, but no change of state. And because this involves specific concept, we use this energy equation. Heat energy equals to mc delta theta. Now let me express this in simple terms. Your Q just means heat energy, and the unit for heat energy is in joules. This joules, okay, is a relative of the concept called calorie in food science. M obviously is mass in units of kg. C is the symbol for specific capacity. The unit is joule per kg per Kelvin. This is your specific capacity, by the way. And this change in theta means change in temperature, obviously, your unit is still in Kelvin. Okay? Now, so you have got this specific concept whereby it's defined as Q equals to mc delta theta from this part. This is where you apply the specific concept. So far, so good. Okay? Now, at this part, this is one part of Q, whereby Q is the energy needed to raise the temperature but not change in the state. Now, at 0 degrees, what happens to the ice? It begins to melt. So it takes some time for all my forces, molecular forces, to really totally melt. And what you can see in physical terms is that originally I have got a full ice like that. Given some time, some part of the ice is melted. This is really pictorially. I do this when I was younger to memorize this concept. Then as time goes on, more my ice gets to be melted and it becomes like that, and I got more water here, and by the time it's fully melted, it becomes here. So this is the point whereby it is fully a liquid stage, but this point to this point, this range, is just a mixture of solid and liquid state. Correct, gentlemen? And obviously, this part is considered melting. Only when heat energy is given at this point will my temperature rise up. Now this part where it's melting involves a concept called your latent heat concept, or you can call it specific latent heat concept, where you use the formula, it's different Q, but this heat energy is given by mL. Now this Q again, heat energy in terms of units of joule, M in units of kg, and this latent heat in units of joule per kg. Now allow me to just introduce you specific latent heat now and specific heat capacity now in a very loose term. We will elaborate more about these two differentiation later on. Okay, but let's just get the general idea first. Now, so this part is melting. Can you see that there is an interchange? Okay, or can anyone tell me what is the interchange between this latent heat and this specific heat capacity concept? For this, something has slipped. Can you tell me what? Come on. Look at this. Here, for this part, temperature rises, no change of state. For here, what happened? Very good. Temperature constant, and there is a change of state. Correct or not? Cool. So this is your latent heat. Now what about this next part? What concept is this? Very good. This portion is again specific heat concept. Why? Because temperature rises, no change of state, and the state is liquid state. And I can go on to vapor state. So my definition for Q, heat energy, is linked to whether it is specific capacity or specific latent heat, or whether it's pure cut, I give it some energy or take out some energy. Yes. C is your specific heat capacity. We will deal more in the next slide. Yeah, that one is latent heat. C in short just means the energy to raise the temperature by 1 degree for 1 kg. In short. Yes. Okay? Now, let's elaborate more about C and L since there are so much question about it. Okay. So, your C, let's reword, is equals to Q over M delta theta after I flip around that equation of Q equal to MC delta theta. Correct, or not, gentlemen? Now, what does C really mean? The definition actually gives a lot of meaning to this. This is just the energy to change 1 kg by 1 Kelvin, and because it's changed in temperature, I could also similarly use 1 degree Celsius change. So what does that mean? It means that, let's say if I have got, let's say for example, 30 joules, and I managed to change, let's say, the temperature for this 1 kg of substance from, let's say, 20 degrees to 21 degrees Celsius, then this C will just be 30. And obviously the units will be joule per kg degree centigrade in this case. So it's the energy to raise the temperature by 1 degree Celsius. So let's make it more exciting. I'm going to change this mass. I'm going to change the temperature as well. Let's see if you can find out what I mean. Let's say the mass of this is, let's say, 4 kg. And let's play around with the temperature. Let's say this temperature started from 30 degrees or 30 degrees Kelvin to, let's say, 35 Kelvin. What is my C? Say again. Very good. Your C will just be your energy needed, okay, which is 30, spread over 5 Kelvin for 4 kg. So 30 over 4 and 5. For 1 kg, yes. Cool? Tristan, okay now?
So it's not like a constant, it's like a value.
Yes, it's obviously a value. Okay? And this is a full unit, joule per kg per Kelvin. Yes. For different materials, your C will be different. But your skin also has got specific capacity.
So it's like friction on different things.
Yes, for different material, you have got different C's.
So it's like specific.
Obviously, right? Because all objects subjected to heat will absorb the heat and gain in temperature. Cool? Okay?
So the unit of Q is still
Heat energy. Your Q is heat energy. Your Q is heat energy. This means
yeah, so
heat energy in joules. Yes. Yeah, yeah.
and the change in degrees Celsius is also
Okay. Now, let's try a question. I'm not going to feed the question to your teams, and then you try to do it. Okay. Okay. Kindly, Tristan, pause.